Hello everyone, welcome to this class. Uh, as I've told in the last class, we'll do some problems related to influence line diagrams, both for statically determinate and indeterminate beams. Okay, so before starting the class, let me briefly tell you what are all the things we are going to cover today. So firstly, I'll discuss some few concepts related to influence line diagram. Then we'll see what are the steps to make the ILD using Muller-Breslau principle. This is a quick method to draw the ILD. So we'll see the Muller-Breslau principle for statically determinate beam as well as for statically indeterminate beam. In between, we'll solve some practice problems also. And then after doing it for the statically indeterminate beam, we will solve some problems, and then we will move towards gate problems. So I'll cover four gate problems from gate 2017, 2019, 2020, and 2014. Okay, so these are all the problems I'm going to cover today. So let's start with ILD. So I hope by the end of this lecture you'll get to know how to draw the ILD for different problems. Okay. Yeah, so what is an influence line diagram? As I've discussed in the last class also, the influence line diagram represents a variation of either reaction, shear force, moments at a specified point as the concentrated unit load moves over the member. So in simple words, when we draw the ILD in a conventional manner, what we do? Suppose we need to draw the ILD for reaction at A. So we take a unit load, concentrated unit load, a point load, and we will move this point load to different points in the beam and calculate the reaction at A. Suppose when the load is at A only, the ILD comes out, the reaction at A comes out to be somewhat here. Suppose the load is at this point, the ILD or the reaction at A comes somewhat here, like the magnitude of this reaction. So in this way, we will join all these points, and that will be the ILD for reaction at A. But in this manner, we have to calculate the reaction for each position of load. Okay, so it's a very time consuming process if we do it in a conventional manner. Okay, but what we will use the Muller-Breslau principle, and using the Muller-Breslau principle we can do the same thing within seconds. Okay, so the second thing I want to cover is the difference between the bending moment diagram and influence line diagram. That is also important. Like bending moment diagram we draw for fixed loading. Please remember that bending moment diagram we draw for fixed loading, while the influence line diagram we draw for moving loads. Okay, so this is the basic difference between the bending moment diagram and the influence line diagram. The third important thing is the ILD is always a straight line for statically determinate structure, while the ILD is curved line for statically indeterminate structure. So these things are also very important. Please note down these points. Next, let us see what is the process to draw the ILD of for shear force, reaction, and bending moment using the Muller-Breslau principle. So we'll see the steps now. So it is for the statically determinate beam. Before starting any problem, please make sure that the beam is statically determinate. Okay. For statically indeterminate things, we will see some different aspects also. So let us say this is a simply supported beam and having end A and B. We need to draw the ILD for reaction at A. So the first step is we will remove this vertical constraint. Okay, so this support is providing this vertical constraint as well as this horizontal constraint, right? So this support is providing the horizontal constraint and vertical constraint, and this support is only providing the vertical constraint. I hope these things you know. Now, what we'll do to draw the ILD for reaction at A, we will remove this vertical constraint from this point A, and then the second step is we will take this point A and we will displace it upward by unit amount. The first step is to remove the vertical constraint or to remove the support here in this case, and then we will pick this point A and we will displace it by unit amount in upward direction. Okay, so the next thing is how to draw it, right? So before drawing the deflected shape, what we will do, we will see what are all the points which cannot move. Okay, so A, we have removed the restraint, but for B, the point is still supported, so we will make sure that this point can will not move anywhere. Okay, now the second step is we have displaced this point upward by unit amount. So this point which was here earlier has now been displaced to here, right? And by unit amount, right? So whatever be the deflected shape now will be the ILD for reaction at A. So the deflected shape of this beam AB will now become like this. If we will displace the point A upward, so it will deflect something like this because point B is still supported. We will join everything now, and whatever we are getting is the ILD for reaction at A. I hope it is simple. Next, let's see if we want to draw the ILD for reaction at B. We will follow the same steps. What we will do, we will remove the vertical restraint from point B. The second step is we will take this point B and we will displace it upward by unit amount. Same step. So before drawing, let us see the point A cannot move anywhere now because A is still supported, and we have displaced this point B by unit amount in upward direction. So we have displaced it to this point, right? Then what is the deflected shape now? The deflected shape will become like this, right? You can imagine also if there is a beam or a bar and it is supported at one end, and we will move the other end upward by one amount, this would be the deflected shape, right? So we'll join everything now, and whatever the thing we are getting is the ILD for reaction at B. I hope it is very simple, right? Now, next, let's see how to draw the ILD for shear force. For drawing the same thing, if we use the conventional method, at least 2 to 3 minutes we would have spent. Okay, but in this manner, we can do this in few seconds. Now, let's see the ILD for shear force. So for ILD, for drawing ILD for shear force, still we have for drawing ILD for shear force, here also we have two steps. The step one is, suppose this is point A and this is point B and this is point C, and we need to calculate the ILD for shear force at point C. The first step is we will make a cut here. We will make a cut at that particular point, and the second step is we will apply the first step is we'll make a cut and we will apply wheels or roller here. Okay, we have made this cut here and we have applied this rollers. Okay, so these, what is the effect of these rollers? Because of this roller, this point, this these two parts AC and CB can now move independently in upward or downward direction. Okay, so imagine some wheels in between this at point C, then these two parts AC and CB can now move independently. Yeah, you can call it a shear release also, right? So in this manner we will do this. Now the second step is the part, the right part we will push it upward and the left part we will push downward. Okay, so now the second step is right part will push upward and left part will push downward. Now let's draw the ILD for shear force at shear force at C. We will restrain those points which cannot move anywhere. So A cannot move anywhere, B cannot move anywhere, right? The second step is, let's see what is the deflected shape. Now we have moved the right part, that is part CB, in upward direction at point C, right? So this part has moved here. Okay, let's join it first. Let's join CB first. So right, next, we have moved the left part, that is part AC, from like in downward direction. So this part C has come in downward direction. Now let's join this also. So we have joined this. Now let us join everything, and whatever we are getting is the ILD for shear force at position C. I hope you are finding it simple. If there is any doubt, you can stop me at any point. Now we have seen what is the shape of ILD, but what is the value of the different ordinates we can also find out. For example, let's call this ordinate as x. Okay, and in total we know that the total displacement has to be 1, like in the case of reaction also this total displacement was 1. So in case of shear force also the total displacement is also 1, right? So if it is x, so it will be 1 minus x, so that the total displacement is 1. Now, how to calculate the value of x? It is very simple. We can use the similarity of triangles, simple geometry. So, okay, so it will be x divided by this length. This length is 7.5. X divided by 7.5 equal to 1 minus x. That is, we are seeing this triangle now. 1 minus x divided by this length, which is 2.5. It's 2.5 here. So, we are getting x is equal to 3 minus 3x, right? We are getting 4x equal to 3. So we are getting x as 0.75. So we have got the value of x as 0.75 now, and we have got, so 1 minus x will be 0.25, right? So in this manner we can calculate, we can determine the shape of ILD as well as we can calculate the ordinates of the ILD. Is there any problem till now? I hope there is no problem. Okay, let me get my yeah. So now we have done with ILD for reaction as well as for shear force. Now let's see how to calculate the ILD for moment. Yeah. Now influence line diagram for bending moment. Suppose again there's a beam. Let's call this point as A, this point as B, and let's call this point as C. Suppose we need to find the ILD for bending moment at point C. So here also two steps are there. The first step is introduce an internal hinge at that point. So we have to determine the bending moment, ILD for bending moment at point C. So we will introduce the internal hinge at point C. The second step is rotate it in this manner. Okay, rotate it in this manner. From this, whatever will be the deflected shape will be the ILD for bending moment at C. Let's see what would be the deflected shape in this case. First, before drawing the deflected shape, let's restrain the points which cannot move. Like point A cannot move anywhere and point B cannot move anywhere. Why they cannot move anywhere? Because they are supported. Now, if we have is this internal hinge right here, and if we will rotate, because of this internal hinge, this part AC and this part CB can move independently, can rotate independently. Okay, they will be together but they can rotate in independently. Okay, so if we rotate it in this manner in the given direction as this, the deflected shape would be, please see, the deflected shape would be like this. Why this? Let's see. Because we are rotating this point C in this direction, right? This direction and this direction, the same direction which we have mentioned here. So we are rotating it in this direction, and this the deflected shape we are getting. Now let us join everything together. If you are not understanding at this point, please do not worry. We are doing a lot of problems today, so you will get to know. Okay. So whatever will be the deflected shape will be the ILD for bending moment at C. Now we have identified what is the shape of the ILD for bending moment, but here we should know what are the different ordinates as well. In this case, like in shear force and in reaction, the main thing was the total displacement should be 1, right? In this case, the total rotation should be 1. So let's call it is theta 1 and it as theta 2. So total rotation, that is theta 1 plus theta 2, should be equal to 1 in order to find the ordinates. Okay, bending moment we have already calculated. In order to find the ordinate values, I'm doing this. So total rotation theta 1 plus theta 2 should be equal to 1. Now theta 1 is, since it is very small, so theta 1 equal to, can be equal to tan theta. So theta 1 is perpendicular upon base. What is perpendicular here? This is perpendicular and this is base for theta 1. Let's assume that this value of this perpendicular value is x. Okay, because we need to find this value only. So theta 1 will be perpendicular divided by base. And what is the value of base here? This value, it is 5. 5 plus what is theta 2? Theta 2 is also perpendicular upon base. So perpendicular is x only, base is 5 here also. Right, so x divided by 5 equal to 1. So 2x equal to 5 and x is equals to 2.5. X is equal to 2.5. The value of ordinate also we have calculated. Right, so these are the three things we have to keep in mind: the ILD for reaction, ILD for shear force, and ILD for bending moment. Okay, let's solve one example problem here. Okay, suppose we have to find the ILD for reaction at A. So what were the steps for finding? Please try to do it yourself also with me. Okay, you'll understand it better where you are getting the problem. Um, so here we need to find the ILD for reaction at A. So the first step was remove this vertical restraint from here or remove the support from here. And the second step is take this point and displace it upward by unit amount. This was the step. Okay, so these two steps are clear. Let us draw it. So before drawing, let us restrain those points which cannot move anywhere. Okay, just for our better understanding. So we have restrained this B point here. B point cannot move anywhere. A point does not have a support now, so it can move upward or downward. D point is free, so it can also move upward or downward. There is no restraint at point D. Now, if there's a beam like this, and if we take point A and move it upward like this, what would be the deflected shape? How it will be deflected? And it is supported at B also, so it will be deflected in this way.
Mhm. You have one appointment
Sorry.
at
Yeah. So this would be the deflected shape. Let us join everything now. Yeah. So this will be the ILD for reaction at A. Right? Since this point D was free to move upward and downward, so it can move downward also, right? So since we are pulling this point A upward, so automatically this point D is going downward. Okay. Just so this will be the ILD for reaction at A. This is ILD for reaction at A. I hope if there is any problem, you can stop me anytime or you can write in the comments also. Okay. The ordinates you can easily find out. If it is 1, so it will also be 1 because both the lengths are same. Okay, let's see another thing. Let's find the ILD for shear at C. So what were the steps? For everything, there are two steps, right? For shear, the first step is to make a cut here like this and to introduce rollers here. Okay, so because of this part, both AC and CB are independent to move in any direction. Now the second step is push this right part upward and pull this left part downwards. Okay, so whatever be the deflected shape will be the ILD for shear at C. Before drawing, let's restrain the supported thing. At A it is supported, at B it is supported, at D it is not supported, so it can move either upward or in downward direction. Okay, now let's move this point C in upward direction and right part in upward direction and the left part in downward direction like this. Okay, let's join everything. If we move this right part of CB in upward direction, it will just make it a little. So here it is upward direction. So let's make this first. Okay. So the deflected shape will be somewhat like this, right? If we'll take this part C and move it upward, the deflected shape will somewhat like this. And the other thing is we'll take this left part downward like this, and let's join the things. So the deflected shape will now be like this, right? We have taken this left part of AC and we have pulled it downward like this. So this is the deflected shape. Now we will join everything and This will be the deflected shape. Sorry, this will be the ILD for shear at C. And if we would have tried it using conventional manner, it would be very time consuming. Okay, please consider it straight at this point. Yeah. So this is the ILD for shear at C. If you want, because in gate the options are given with only in which you have to determine only the shape of the ILD, then you can leave it there only. But if the different options are same, like the shapes are same and the ordinate values are different, then only you should calculate the ordinate values. Okay, you have to just save your time. First see the question and look at the options. Okay, if you do not need to if you do not require to calculate the different ordinates, just leave it there and take the correct answer. Okay, if the ordinate calculation is necessary, then only you should calculate. Here also the ordinate calculation is easy. Consider this as x. Okay, so total displacement should be 1. So if it is x, it is 1 minus x, right? So you can calculate the value of x as in the previous case. So x divided by this length is 2.5. 2.5 equal to, and 1 minus x divided by 2.5. This, since these two length 2.5 were same, so the value of x will come out to be 0.5. Okay, so if it is required, then you can calculate the value of this ordinates. Otherwise, in most of the questions, you will only be asked to determine the shape of ILD. Okay, let's so share is done. Now let's see one problem related to moment as well. Okay, so in this question, it is asked to determine the ILD for bending moment at point C. So what we will do, we will introduce, the first step was introduce a internal hinge at that point. So we have introduced an internal hinge at C. Now the point C, AC, CA and CB are independently can rotate. Okay, so we have introduced this internal hinge here, and then we will apply this rotation in this manner. Okay, now let's restrain the points which have supports. So we have restrained A and B. Now let's see, if we will rotate part C in the given manner, what how will the deflected shape look like? The deflected shape will look like this. Okay, after drawing the deflected shape, just make sure that your rotation part is satisfied. Okay, okay, so please okay, it's done. Just join everything. Okay, so this is the ILD for bending moment at C. I'm just showing you that this part is rotated in this manner only. So we have to rotate these two parts in this, in the given manner. Yeah, so they are in this manner only. So let's call this as theta 1 and let's call this as theta 2. What is the condition here? Theta 1 plus theta 2 should be equal to 1. Okay, so let's, if we need to calculate the ordinates as well, let's call it as x, right? Let's call it as x. So theta 1 is tan theta is equal to tan theta, and tan theta is perpendicular upon base. So it's perpendicular is x and base is 2.5, right? So it is x divided by 2.5. Theta 2 is also x divided by 2.5. Theta 2 is perpendicular and divided by base, so x divided by 2.5, and it should be equal to 1. So 2x equal to 2.5. Yeah, it's good, Rahul. And x equal to 1.25. That's okay. So you will see that in gate, in 2014 question, the question was like that, was like to determine the shape of ILD only. But in the recent years, these kind of simple questions are not coming. The question, it has shifted to like determine the shape of ILD as well as determine the coordinates ordinates of different points, so that you could determine the maximum value of shear force in bending moments. Because then they have to, because in this case, what is the value of the load which we are moving? It's a unit load, right? But in the questions, they have given the value of some loads. Okay, so in that case you are bound to determine the value of ordinates as well. Okay, like in 2014 simple question was there in like in the recent years, like in 2020 and 2021. So you have to determine the shape as well as you have to determine the ordinates, plus you have to determine where you have to keep the loading. Ma'am, what will be the code at the last point? Yeah, you can also determine at this point also if you are required. Like he's asking, I think, this point. So let's call it as M. So from this similarity of triangles, you can calculate x divided by, and now x you know, right? X is 1.25, I guess. So x was coming out to be 1.25. So x divided by this 2.5 equal to m divided by this length. So these two triangles I have considered, this triangle 1 and this triangle 2. So x, this length x divided by this length, and m divided by this length 5. So m, that you can calculate the value of m, 1.25 into 5 divided by 2.5. Yeah, I guess it's again coming out to be 2.5 only, right? So in this way you can calculate the different ordinates. Okay, so ordinate calculation is not at all difficult because it's based on simple geometry. Okay, so like we have done some example problems as well, but before doing some other problems, let's move to gate problems, because I guess otherwise the time is less. So if we are done with the gate problems, we'll again these problems. But before the gate problems, let's do the statically indeterminate thing as well. Okay, so the most important thing regarding the statically indeterminate problem is, in the statically indeterminate problem there will be curved lines for ILD, right? So whenever you are seeing a curved line for a statically determinate problem, just remove that option then and there, because for statically determinate problem curved line in ILD is not possible. Okay, so it is very simple. Another important thing for statically indeterminate, problem is, in this case you can just determine the shape of ILD. For calculating the different ordinates you have to do some more calculations, which is not at all necessary for gate. Okay, so in gate maximum they can give you, because that calculation is again very lengthy. So in maximum you can get a question in which you have to determine the shape of ILD for an indeterminate problem, right? Okay, so please keep that in mind. Okay, so it's very important that before starting any problem, just make sure that beam is statically determinate or it is statically indeterminate. Just make sure that thing. Okay, yeah. The another thing is, let's see how to determine the ILD for reaction at A. Okay, the process is again it's very similar. It's the same to that in determine for determinate beams. Okay, so for drawing the ILD for reaction at A, what we'll do, we'll remove this support, we'll remove this vertical restraint, and we'll take this point and move it, displace it upward by unit amount. Okay, so let's see what happens. Again, before drawing, let me restrain this point B and C here. Okay, now please just imagine, there's some imagination is required. So if we move this point A upward direction, okay, and these points have to be fixed, then the shape of ILD will be something like this. Okay, it's not very straight. Yeah, so this I've not drawn very um, good lines, but okay, you're getting it right. So it will be something, some curved line. Okay, I'm just removing it for now. So this would be the deflected shape in this case, right? I hope you agree, right? So no, it will also be curved. It will also so it's always curved, right? Okay, for for indeterminate problem. So let us join everything. Okay. But you will just get an idea of how the ILD will look for statically indeterminate problem. You cannot calculate the exact values because it is curved. At every point it is changing. Okay, so you cannot calculate the exact value. Yeah, but in I've read it somewhere that it's a 3-degree curve. I'm not very sure, but it's a 3-degree curve. You can check it. Okay, but it doesn't matter. Okay. For stress function, the Muller-Breslau principle says that ILD will be a 3-degree curve. You can check that also. Okay. Yeah, so it is done for reaction. This next for shear force at D, suppose we need to calculate the ILD for shear force. The steps are same here. We'll cut it at this point D, and we will uh, move this part upward and this part downward. Okay, let's follow the usual thing. We'll restrain point A, point B, and point C, because these all points are supported, so they cannot move anywhere. So I've make sure that they are not moving anywhere. The next step is how will this part deflect, this part deflect when we will move this point D in upward direction. Okay, so it will deflect something like this. Okay, yeah, it will deflect something like this. I hope you agree. And this part will deflect like this. So you cannot tell whether this curve will be like this or will be like this. So it is like this, like this. Okay, so you have to see that like this. So as I've told earlier, you in for statically indeterminate beam, you can just get an idea what should be the shape. You cannot determine what is the exact curve or anything. Okay. So maximum you'll get a question like this, in which you'll get you need to determine the shape of ILD only. Okay. So the steps are same for both statically indeterminate and determinate problem. And 99% of the cases you will not get a statically indeterminate problem, but I guess in 2022 or 2021 you have got one question, but in that question also you need to determine the shape of ILD only, nothing more. Okay, the next thing is moment. So the steps are same. We will introduce the internal hinge at point D. Suppose we needed to determine the ILD for bending moment at D, so we will introduce the internal hinge at D, and we will rotate it like this. Rotate it like this. Okay, now I'm restraining the points A, B, and C. If I will rotate this part DBC in this manner, so what would be the deflected shape? The deflected shape will be like this. Please pardon my drawing, but it will be like this. Okay, and for AD, if we'll rotate it like this, the shape will be like this. I hope you can imagine these things. Okay, so we have rotated it like this and like this. So let's call it as theta 1 and let's call it as theta 2. And this is the ILD for bending moment at point D, the shape of ILD. So at least for indeterminate problems also you can guess what is the shape of ILD, although you cannot determine yes, like at this point the what are the different ordinates. Okay, there is a method for that also, but it's very lengthy. You will not get that in GATE. Now we before let's do this practice problem, one more practice problem, and then we'll move to okay towards the GATE problem. Let's quickly draw this. Okay, okay, let's do this problem. Okay, if we require to determine the ILD for reaction at A, it is looking like very complex problem, but it's very easy. Okay, so the steps are same. We will remove this support at A, and we will take this point and displace it upward by unit amount, right? Let's fix all the other points which cannot move. B can move, right? B can move anywhere. Okay, it will move or not, it depends, but it can move, right? Point C, let's call it as H and I, let's say. The point H cannot move anywhere and point I cannot move anywhere. So I've fixed all the points which cannot move. The other thing is we will take, just imagine, okay, just imagine this long bar keeping, yeah, he's right. So let's imagine this long bar here. We are taking this point A and we are displacing it by unit amount, and there is an internal hinge here. So from hinge, this part will simply move like this. Other part will remain undisturbed, right? Imagine there's an internal hinge and you're taking this point in upward direction, so it will displace like this. Other part will remain undisturbed, right? So this will be the ILD for reaction at A. So for solving this kind of problems, you have to use your imagination a little bit. So other points I'm just joining. Yeah. So this will be the ILD for reaction at A. As simple as that, right? So just practice a lot of problems for this. Okay. Okay, so let's see some gate problems now. Or let me draw some question or see. Yeah, let's draw see the gate problems now. After that, if time permits, then I'll again get back to these problems. Okay, so this is a gate problem. Yeah, you can ask Binoy. Have you on Aston? Oh, okay. Okay, yeah, got it. Okay, have yeah, I should tell that to you. Is it a determinate or an indeterminate beam? Where it was, yeah. So please make sure before starting any problem that beam is determinate or indeterminate. So let me tell you whether it is determinate or indeterminate. Okay. The quick method to determine for a beam is that a statically determinate or a simply supported beam is always statically determinate, that you know, right? A simply supported beam is statically determinate. So by adding the support, we are adding the restraints, okay? And by adding the internal hinge, we are removing the restraints, okay? Or degree of indeterminacy. So in this case, if we are finding the degree of indeterminacy, so at this point, if it is a simply supported beam, it is statically determinate. Okay, we have added one support, we have added this support C. Okay, we have added this support, let's call it as H. We have added this support H. So now what is the degree of indeterminacy? Earlier it was statically determinate, that is di was degree of indeterminacy was 0. Now we have added 2 more restraints, so degree of indeterminacy becomes 2. Okay, by adding the internal hinges, we are removing or we are balancing out the restraints. So I have added this restraint at B, and I have added another restraint here at let's call it as I. So I have added two more restraints. So I've removed this. Now degree of static indeterminacy is 0 in this case again. Okay, so this is a quick method to determine the degree of static indeterminacy, or you can maybe, I hope you have studied degree of static indeterminacy, or maybe I'll cover it in coming lectures also. So this is the quickest method by which you can determine. So let me ask you for one problem. Um, okay, not this. Say it's roller here. Is it statically determinate or indeterminate? This problem. You can answer in the comments. Determinate. Why? Because when it was simply supported, it was determinate. So degree of indeterminacy was 0 in in this case. We have added one support here, so I have added one support plus 1. I have added this internal hinge also here, so I have minus 1. Internal hinge will cause minus 1 and adding the support will cause plus 1. So finally it will become 0, right? If this internal hinge won't be here, so degree of static indeterminacy would be 1, because I have added two support but I have removed only one restraint, so it would have become 1 in this case, right? So these things you should check before attempting any problem, but and usually it will be very clear to you that beam is statically determinate or indeterminate, because these like this would not be a problem for you, I guess. Yeah, so let's start with the gate question. So just tell me, this beam is statically indeterminate or determinate? Quickly in the comment section, this beam is statically determinate or indeterminate? Great, it is determinate. Okay. Please revise this concept of determinate or indeterminate, and I'll cover some of them in the next class, coming classes also. So quickly, just let's take this question. So it's a GATE 2017 question, question number 41 of set 1. Consider the beam ABCD as shown in the figure. A beam is given to us for a moving concentrated load of 50 kilonewton in the beam. The magnitude of maximum bending moment obtained at support C will be obtained at support C will be. So here in this case, how do we know that we have to make an influence line diagram? Because nothing is written that make an ILD or determine the ILD or anything is not written. We will get to know by seeing this term, moving concentrated load. So whenever there is a moving concentrated load and we need to determine the value of either maximum bending moment, shear force, reaction, anything, it means that we have to draw the ILD at that point. I hope it is clear. Whenever we see that there is a question of moving concentrated load or moving uniformly distributed load or any moving load, then we have to draw the ILD in that case. Okay. And ILD for what? ILD for reaction, for shear force, or what? So in this question, ILD for bending moment, and at what point? At support C. So we have to determine the ILD for bending moment at C. Okay, so directly it is not given, but in this manner they have asked us. Then after drawing the ILD for bending moment at C, then we will see what is to be done next. Okay, other calculation we will see, but at least we should know what we have to do, right? We have to do ILD for bending moment at point C. It's a 2 mark question, by the way. Okay, now how to draw the ILD for the steps are same. We will introduce an internal hinge at point C. We'll introduce an internal hinge at point C. Please note that I haven't removed the support. Okay, in bending moment we do not need to remove the support, we just have to introduce the internal hinge. So support is still there. Okay, this point C cannot move up and down because it is still supported. We just have introduced this internal hinge here. The second step is to rotate it in this manner. Okay, we have rotate it in this manner. Now the thing is very, I have asked you this beam is statically indeterminate or determinate. Now you'll see how it matters here. Okay, so we know that this beam is statically determinate, so any part cannot be curved here. Okay, if any part of a determinate beam is curved, then we have, it means that ILD does not exist for that point. Okay, if any part for a determinate beam is coming out to be a curved line, it means that ILD does not exist for that particular part. This is a very important point. Please keep that in mind. I'll repeat again. If any part of ILD for a determinate beam is coming out to be a curved line, it means that ILD does not exist for that particular point. Okay, let's see how. So I have done all the 2 steps. I've restrained the points which cannot move anywhere like this. Now the second step is how will it look like? How will the deflected shape look like? So we have I have taken this point C and I have rotated it like this. So let's see how will the deflected shape will look like. Oops, sorry. The deflected shape will be like this for this part. For ABC part, if I am taking this part C and I am rotating it in downward direction like this, and anti-clockwise direction like this, so the deflected shape will be like this. Let's call it as theta1 for now, right? The second step is I have to rotate the part CD as well, right? But if I'm trying to rotate this part CD, how it is coming out? What is the how it is coming? It is like, it is becoming like this way, right? It is becoming curved. Okay, if I'm trying to rotate it like this, because in this part A there's an internal hinge B in between, so it was coming like this. Okay, but for part CD there is no internal hinge in between and I'm rotating in this way, but it has to be here also, so it is coming like this curved part. But I have told you earlier that for a determinate beam, ILD cannot be a curved line. So if ILD is coming out to be AB should not move. A should not move, B can move. B is not supported. So B can move, A cannot move. I have not moved A anywhere. B can move up and down. Okay, and B is an internal hinge, so it can rotate also in any manner, right? And here, so it if uh, for part CD the ILD is coming out to be curved line, so this means that since this beam ABCD is a determinate beam, so ILD cannot be a curved line for any part. If ILD is coming out to be curved line, this means that ILD does not exist for that particular part. So for CD part, the ILD is coming out to be this curved line, so it means that ILD does not exist for this part. What does it mean actually? It means that it will be straight line here. It will not, there will not be any deflected shape here. So let us join all the points, and this will be the final ILD for bending moment at C. Okay, so you have to just revise it again. Okay, this was important thing here, that for part CD, since ILD is coming out to be a curved part, so ILD does not exist for part CD. And the another thing was the total rotation, that is if both the parts were rotating, so theta 1 plus theta 2 comes should be 1, right? But here theta 2 is already 0, so theta 1 is 1. So is this theta 1 is 1. This is also very important. Okay, so let's see, they have not asked a question directly, so like a very simple question, although the steps for drawing are same, but they have like added some more complications here, right? So this is one here. Okay, now using this one we can calculate this ordinate as well, because here we need to determine the maximum bending moment for 50 kilonewton, so we need to know the ordinates as well. Okay, so like it is, if it is 1 and this is 4, right? So it will be 1 tan theta equal to, sorry, theta 1, which is should be equal to perpendicular upon base, right? So theta 1, this is theta 1, right? 1. And what is the value of perpendicular? This is x, let's assume it as x. And what is the value of this base? The value of base is 4, right? So x will be 4 theta 1. What is the value of theta 1 here? 1. So x will be equal to 4, right? If there's any confusion, you can ask me. So we have calculated the value of x as well, and it is 4, right? Now everything is done. Now the things are very simple. I have determined the ordinates as well as I have determined the shape. Now what they are asking? They are asking where should be, for a moving concentrated load 50 kilonewton, what is the magnitude of maximum bending moments? It means that where should we keep this 50 kilonewton load so that we get the maximum value of bending moment. So for that I have drawn the ILD for bending moment. Where should I keep this 50 kilonewton load now? I have to keep, for maximum value of bending moment, I have to keep the 50 kilonewton load at here, right, at B. Okay, because why? Because I have to, how will I calculate the value of bending moment? I'll multiply this load which is given to me, that is 50 kilonewton, with the ordinate at which I am keeping this load. So if I'm keeping this load at this point, because the magnitude of this ordinate at B is maximum, so I have to keep the load at that point to get the maximum bending moment. So I'll keep this load at B, and whatever will be the value, 50 multiplied by the ordinate at that point. So ordinate at point B is 4. Ordinate of this ILD at B is 4. So I'm multiplying it with 4. So whatever will be the value of bending moment will be the maximum bending moment, and answer is 200 kilonewton meter. So this is our answer. And if it is a fill in the blanks type of question, so it will be 200 here. See, the question in this question, in the recent year, they are not directly asking how that you have to draw the ILD and then you have to do anything, but they have simply, but by simply seeing if there is a moving load written, then it means that you have to draw the ILD. Okay, and then where, yeah, that is also important point, is right, that firstly we should know that beam is statically determinate or indeterminate. Okay, if, yeah, so if this beam would have been statically indeterminate, then this curved part would be there, but this beam is statically determinate, so this curved part cannot exist, and that therefore we have removed it. Okay, so these few points you need to keep in mind before starting a problem. So let's quickly revise. After seeing a question, if you are seeing that moving load is written there, then you should know that you have to draw the ILD. Okay, then the second thing is where to draw the what at what for what quantity you have to draw the ILD. For reaction, for bending moment, then that you will get from the question, that here we can see the maximum bending moment. So we have to calculate the bending moment, the ILD for bending moment at what point? At support C. So we know that we have to draw the ILD for bending moment at support C. The second thing now is whether this beam is statically determinate or statically indeterminate. So that point we should keep. So we know that this beam is statically determinate. So we should know that any curved part cannot exist here, right? So like this we can draw. Okay. I hope it is clear. Okay. So yeah, for this question also, it's a 2019 question. Let's see. Here also, it is, I guess it is nowhere written that you have to determine the value of, so you have to determine the ILD. It's also a 2 mark question, right? So it was given that a long uniformly distributed load of 10 kilonewton per meter and a concentrated load of 6. So they have included, like in 2017 there was just like concentrated load, but in 2019 they have added the concentrated load as well as the UDL also, right? Yeah, if that they will not give any beam which would be statically indeterminate, then because in that you have to you have to make a lot of calculations to determine the ordinates. Okay, so they would not give such problem. That is a different thing. For statically indeterminate problem, maximum they'll give you the question in which you have to determine the shape of ILD. Okay, yeah. So in this question, they have added this. So by year, they are adding the complexities, right? So a long uniformly distributed load of 10 kilonewton per meter and a concentrated load of 60 kilonewton are moving together. So at that point, you should know that you have to draw the ILD. Okay, if you see the word moving. Okay, so they are moving together on the beam ABCD as shown in the figure. The relative position of the loads are not fixed. So it is not fixed that like we have two loads. One is a uniformly distributed load and we have a concentrated load 60 kilonewton, and this is 10 kilonewton per meter. So their relative positions are not fixed. It means they can, like this, if the distance between them is x, so the value of x is not fixed. This 60 kilonewton load can be here, it can be here, it can be anywhere. So its position between these two loads is not fixed. Okay, the second thing is the maximum. So we know that we have to draw the ILD, but at for what quantity? Okay, so we have to draw it for shear force. Okay, so shear force, but at what point? For internal hinge at B. Okay, so first from the word moving, we know that we have to draw the ILD. Second, we know that we have to draw it for shear force, and at what point? At internal hinge B. Second point is whether the beam is statically determinate or indeterminate. Whether this beam is statically determinate or indeterminate. Please write in the comments fast. Determinate or indeterminate? Same beam as before, right? It's the same beam as before. So earlier beam was also statically determinate, and this beam is also statically determinate, right? So it's maximum, like 99 or 100% of the cases they'll give you the statically determinate beam only for this huge calculations. Okay, so they'll give you, but please make sure that this is statically determinate or indeterminate. So it is statically determinate, so now we can proceed. Okay, so we have to draw the ILD for shear force at uh, okay, yeah, maximum value of shear force caused at internal hinge B. So at internal hinge B, we need to calculate the ILD for shear force. So we have to find the ILD for shear force at point B. So what is the steps we need to follow? We will, yeah, we will apply this load here. So I guess the time is very less. Let me uh, just yeah. So we have just few minutes now. Yeah, let's quickly do it this question only. Okay, so next two other questions also remaining. Let's leave it for now. The second thing is we have to make a cut here and we have to introduce the roller here. right? We have to introduce the roller here. The second thing is we'll move this part upward and we will move this part, right left part, downward. So this was the common step for ILD. Is someone asking any question? No, right? Yeah. So we have, like for shear force, what we have to do, the first step is we have to make this cut and then we have to introduce these rollers. The second step is we have to move the right part upward and the left part downward, right? Now the thing is, let's do how the things are deflecting. Let's restrain this part A and this part C and this part D. Okay, other than these 2 points, every point can move up and down. Let's see left part. That is part AB first. If we deflect it in downward direction, what would be the deflected shape? The deflected shape would be, you have to check your answer. I guess it is not right. Just check it once. Yeah, so deflected shape will be like this. Okay, now if we move the left part, this right part upward, please see what is a deflected shape. If I am trying to move this part upward, so deflected shape would be like this. I hope you agree. If I'm taking this part B and moving it upward, so the deflected shape for part BCD will be like this. And it is a determinate beam. Can a determinate beam have this curved part? No, right? If the determinate beam is having a curved shape for any part, it means that ILD does not exist for that particular point. So it's a very important point. Like, see, this point is, can you see the pattern into 2017 also, as well as in 2019 also? They are checking this thing. Okay, they are checking that whether you know that or not, that for statically determinate beam, curved part cannot exist. So the ILD does not exist for this part simply. Hmm? Now let's join all the other things. This is the only thing that can, the only thing that they can ask here. So if you just remember this thing, okay, the curved part will not exist for this. Okay, so the total displacement have to be 1. Okay, so here the up this right part is not moving up anywhere, so this total displacement should be 1. Okay, so this is the ILD for shear force at B. Please practice these kind of questions. They are not giving to, they will not give you the straight word, straight questions. They'll add some complexities. Now I have drawn the ILD for shear force at B. Now quickly let's see where we have to keep the load. So we have to keep the load such that we'll get the maximum ordinate value. And the other thing is, the positions are not fixed, like we can place it anywhere. Let's see if you agree with me or not. I want to place this load here, uniformly distributed load here, and I want to place this 60 kilonewton. Where should I keep this 60 kilonewton load? I should keep the 60 kilonewton load where there is the maximum ordinate. So where is the maximum ordinate? At point B only, right? Great. So it is here. So it is the maximum ordinate, and I'm keeping the 60 kilonewton load here, and I'm keeping this 10 kilonewton per meter here. So that I'm getting the, just to make sure that you'll get the maximum value, right? If I would have kept it somewhere any other point, the maximum value won't be there. Okay, let's quickly calculate it. How to calculate this? Whenever you are calculating for this UDL, just multiply it with the area of triangle, and whenever you are calculating the values for the point load, multiply it with the ordinate value. Just keep this thing in mind. I'm calculating for 10 kilonewton per meter first, that is the UDL, so I'll multiply with the entire area of this triangle. What is the area of this triangle? Half. What is the value of base? 2. And what is the height? 1, right? And whenever I'm calculating it for the point load, I will simply multiply it with the ordinate value. So 60, what is the ordinate at 60? Or the ordinate at 60 is 1. So it is 1 here. So I'll calculate it. So it will come out to be 70 kilonewton. What I needed to calculate, right? Yeah, maximum shock. So it's coming out to be 70 kilonewton here. Yeah, so the answer is 70 kilometer. I hope it is clear. If you see the pattern, or I'll just quickly show you the 2014. You just see this question, right? In 2014, it's a very simple question. For this question, they have asked the ILD for shear force at B, what would be the shape? So they have given different shapes. You just need to determine the shape for ILD. Very, very simple question. But now For in the recent years, they are not giving such kind of questions. Okay, so please see this question also, GATE 2020, set 1, question number 28. Please see this question for practice. Please note it down. GATE 2020, set 1, question number 28, and GATE 2014, set 1, question number 12. Okay, so these two questions just for your practice. So like in alternate years, at least they are giving this question of ILD, and most commonly for these days they are giving this kind of questions in which directly they are not saying that you have to draw the ILD, but indirectly you have to calculate it, and it's a very easy question. The same concept is there, right? For determinate beam, for some part they are giving like curved part should come, but it is not coming, so you have to remove that part and do the calculations. Okay, so these two questions were quite similar question. Yeah, and in 2021 there's also one question, but it is for indeterminate beam. You can do that for practice also, but in that question you just need to determine the shape of ILD. For that you do not need to do any calculations. Okay, for indeterminate beam they won't give you any calculation part because it is very time consuming. Okay, so just practice for determinate as well as for indeterminate beams, and just keep these few points in mind. First of all, just make sure that beam is statically determinate before solving the problem. And the other thing you have to keep in mind that directly they will not give any question to draw the ILD. Just note that this from this moving part that you have to draw the ILD. Okay, I hope this is clear, and the time is also up. So are there any questions, or should I close the session? Please practice. Okay, these two questions are which I have not covered today. Okay, so okay, that if it is clear, so just whatever topics you are covering, just if you are doing for ILD, just do all the question, like just see in 2014. I think you must be having a book in which all questions, all years question would be there. So if you are learning ILD today, just do all the questions of ILD today itself, or tomorrow in the weekend just complete ILD. Okay, the benefit is you'll get the practice. Second thing is you'll get the pattern how the things are coming these days. Okay, so this is very important. So today you have learned how to draw the ILD for beams. Do every possible problem of ILD so that everything is clear then and there. Okay, I hope it is clear. Thank you for listening. If there are any questions, you can ask. I guess there are none. Okay, so please don't hesitate to ask anything. You can ask me anything in the comments. Okay, if you do not want to ask like in the mic, then you can ask in the comments also. Okay, then thank you so much. Bye for now.